This is project 1 video number 3, the one in which we do the documentation. I'm going to get it started, but I won't make you wait for me to type in all that. Okay, so I've typed in what E-field does, calculates the magnitude and direction of the electric field at position 0,1 meter due to 101 charged particles, each having charge Q, provided by the user of this function, spread out uniformly along the x-axis from x is equal to 0 to x is equal to 1 meter. And then we need to do input variable percent tab Q charge of each charged particle it'll have the same value of charge and then output variables. First element of that array, and it's pretty clear what the output variables are, so I just need to define them. E equals magnitude of the total of the electric field at 0,1 meter. Oops. So that point on the y-axis, and theta angle in degrees of electric of the electric field. Plus x direction with counterclockwise being positive. That is the mathematician's convention. And let's see if we can tab that over. There we go. So theta is angle in degrees of the electric field at 0,1 relative to the positive x direction with counterclockwise being positive. Okay. Y equals 1. That's pretty clear. Let's see if we see. Alright, I think I'll tell them yeah, theta each element is angle of the contribution to the electric field at 0,1 meter by the corresponding due to, let's call it, contribution by, contribution of, due to the corresponding particle. So let's try to wrap comments there. That's not working for me. So I'll move the percent over there to be even with this. Is that is angle of wonder. So the contribution to the electric field due to a single particle is an electric field vector. But it's not the total electric field vector. All the individual electric field vectors, all the individual contributions add up to the total. So each element of this array is the angle of the contribution to the electric field due to the corresponding particle. So the first element of this array contains the angle of the electric field due to the first particle. Okay. So this is pretty obvious. I think that you got to flip that if the charge is ooh, that's almost. Yeah, it's not really true until I get down to here. So let's try 12x. Of theta array text wrap comments. So each element of the theta array is angle of contribution to the electric field and to the corresponding particle. Okay, I think that required a little bit. So this gamma ray is pretty clear that it's being used to build up to determine the theta array. So I think we're good there. This is obviously the array of EX values. And yeah, I think everything else is pretty self-explanatory. I guess I better say who wrote it. Don't forget that. Can't get credit for the documentation if you don't put your name. I'll put attribution down here. Outside resources. Oops, that's a C. Used in writing this code. That would actually be enough. Like if you did it all on your own, the way I did it, and you used the help function within MATLAB, you don't really. That's not an outside resource. That's an inside resource. And it's assumed that you use the manual when you're writing code. You know, the help function within it. But I'm going to go ahead and put that anyway. So a little bit of overkill. I choose to engage in a little bit of overkill in the attribution, and that's certainly fine too. But I did use the help function within MATLAB to get information on the ATN2 function. Okay, no outside resources were used to write this, but I did use the help function within MATLAB to get information on the ATN2 function. Alright. So I'm going to save it. I'm going to move this over. You won't be able to read all the comments. If I have to edit them, I'm going to go back. But we do want to make sure it still works. Doesn't print anything extra. By the way, let's try a negative value of charge and make sure it makes sense for that. So it's the angle I'm worried about. So the magnitude is going to be the same. That makes a lot of sense. But how about the angle? So it's saying the angle is still 112 degrees. This is bad news. So I'm expecting if everything is negative, then it's no longer 100. Go back to our original picture there. Good thing I checked that. So with everything being positive, the total electric field is up in some direction, kind of like the one I drew that there. Definitely not directly away from that, but up and to the left. And if all these charges are negative, then it should be down and to the right. So that's not the way it turned out. And so we better fix that up. It might have to do with my vector component diagram here. Is going to be a little bit different if the electric field is negative. So I think that goes all the way back to our pencil and paper part. So if the electric field is coming down in this direction, yeah, I wonder if we just take whatever the angle is how to use this angle and use that projection idea, then I think I'd be okay. So let's see. It's actually what I got. Oh, I see. That was for my test case. Okay, I'm going to pause the video while I troubleshoot. Alright, I think I'm going to have to look at the code itself. And let's make sure that this works. So all these angles, if Q is equal to 0, should be down and to the right. It should correspond to down and to the right toward the corresponding charge particle. So let's print out the theta array. I think I'll do it separately, I think right after that. Theta array. So just that troubleshooting line. And I think I want to cut down on how many of these we're printing out, so maybe I'll make it 6. I think that might all fit on one line. Alright, so let's run that. And yeah, that makes sense. The first one would be straight down, and then everything else down and to the right. But I'm coming up with a bad angle there. So I'd say the theta array is making sense for negative angles. Or for when the charge is negative, the angles make sense to me. So I think I can take that out. And I'm expecting the X array then to have positive values. Let's go ahead and print that. And I'm getting negative values for the X array. And as I look at the cosine function, I think I gotta draw that on here. See if maybe I was wrong in what I was expecting. So the cosine function goes something like this, and this is, well, that wasn't well drawn. So that'd be 180, 270. I think I know what it is. 90. So when I was calculating the magnitude of the electric field, I needed the absolute value of the charge in there. So I've got a minus sign in there if it's negative, and I was trying to find just the magnitude, and so I'll go absolute value of all of that, and I was taking care of the direction manually. So that was the problem. Sometimes that was turning out to be negative, so my E array would have been off on that one. All right, let's try saving that. Let's try seeing if I need to fix something up in my original pencil and paper work. Oh, I've got, it was actually right. So if I copy that down here right, then I'm okay. Yeah, I had it right up there, but in my code outline I didn't. So I need that, and then to make that consistent with the way I just wrote it, which was a copy of the way I'd written it a little bit earlier in the pencil and paper part. I'll put that. Absolute value Q, and let's see if that fixes everything up. So that gives me a negative angle with respect to the x-axis. That's perfect. So in other words, I would expect it to be down into the right. And so I don't need these printouts at this stage. Again, I was just getting the magnitude of the electric field. It took care of the direction explicitly with this at the 180 degrees. So in essence, I think I was double counting that minus sign for the negatively charged particle is what it amounted to. So I'll save that. It's already been saved. Go ahead and run it. Now I'm getting no extra printouts. Nothing extra being printed out. But I am getting the negative there. And before it was 112. Actually, what were the results I was getting when it was positive? 112 was the angle. I go, well, I'm expecting, since I use the same magnitude of charge, it'll just be 112 minus 180. Every vector gets its direction switched, so that should switch the total vector's direction. And it might be it's a little bit off, but yeah, I think I would expect it to be in about that direction, but not necessarily the exact opposite direction. So I flip every vector that's going into the sum. We get something that's pretty close to the opposite direction, but I think we're good there. So with that absolute value sign in there, I tend to believe what we got. Oh, I know what's going on. Because I am puzzled there. I'm thinking if I flip every vector, I really should get the exact opposite direction. But comparing the electric field due to 6 charged particles with that to 101. So let's go back to the 101 that's required. I had it at 6 just for troubleshooting purposes. And then try running that again. And I'm getting that minus 67.6715, which is indeed what I was getting when I had positively charged particle. But since every single contribution is being flipped, that was right. If you flip every single vector, then the sum is going to be in the exact opposite direction, 180 degrees off. So those two are agreeing exactly now. Alright. So now it's all making sense. Code the way I originally had it was not working for negatively charged particles, and now it is. So let's go through the checklist. Pencil and paper, it's going to have the algebraic solution leading up to it. So I derived all the equations. I think I'm good there. Diagram had that calculated values of the x and y components due to that one charged particle, the last one, at that location when its value is that. That's the value I've been playing with. So they serve a check. We did that. For each function, the outline of the steps, I definitely got that. Okay, program part. Reasonable attempt at writing it. Got that. Works properly. Do what it's supposed to do. Fix that up so it's doing what it's supposed to do, or as far as the checks that I've been able to make so far. and prints nothing extra. Let's make sure with the last run that I made, I was doing it with the negatively charged particle. It printed nothing extra, just the answer. Just what the return variables, and I had to type this part in to make it so it would do that. Alright. Nothing to the command window. Good. Other than the returned array, and it only does that when I want it to, when I make it. Just prints that first element if you don't do that. Then you got your name in every file. You got my name in there. Documented. Comment stating what the function does. That was this first one. Takes arguments, what each argument is. Takes one argument. That's the input variable, I call it. For the case of a function that returns one or more values, say what each one is. Okay, got that covered. If it includes segments that aren't self-explanatory, I felt I had one little piece that wasn't self-explanatory. It was actually the segment wasn't self-explanatory because it wasn't clear what the theta array was, so I made it clear what that is. So I think that's good. And then attribution. Make sure you don't just copy mine. Remember, it's going to be your own attribution written in your own words. No credit if it's just a copy of mine. Mine's got to be identical to mine, so mine's cool. But make sure that you pay attention to that. And then that does it. So that's a wrap for Project 1, video number 3.